So the recording has started. Okay. So hello and welcome everyone. Welcome to this lecture. So we will be basically continuing upon what we built upon last time. Uh, so let me share my screen. By the way, is there any doubt from last time which we need to take out?
No, last lecture
Okay.
was clear to me.
Okay. 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 So let's see. Right. Okay. So last time what we did is it coming from my tab, I think. Wait. Is it okay, it's still coming. Just a second. Hmm, what do I need to make this thing silent? Hmm, um, completely on mute. Is, is there any echo you can hear? Just
No,
no.
yeah, voice is clear now.
Okay, fine, fine. Just okay, fine. I mean, let's get started with what we did last time. So we started with this concept of, so we introduced this concept of PGMs, right? Probabilistic graphical models. What are PGMs? Well, they're nothing but a set of random variables which are associated with a graph structure. Particularly, they are associated with a DAG-like graph structure. That's the broad idea, right? Uh, Now, why is that of interest to us? Well, usually, practically, we do know the structure. Like this graph structure is what we know. And for example, we know what variables influence what other variables. And, you know, that is something that we know without doing anything. So in those situations, these graph structures sort of help us in writing the joint distribution and give us sort of insights into what is it that but basically gives helps us in simplifying things. So for example, well, I mean, for any given joint distribution, you always have a trivial PGM which is given by your Bayes rule. Okay, so Bayes rule always associates this kind of DAG structure on top of your random variables. However, if you if you have some other DAG structure on your random variable, something like this, it might help you to simplify the decomposition, right? More than that, it like what we are interested in particularly is the generative view of PGMs. Okay, so basically, what it means is that so there is some random variable or variable of interest to us, right? Meaning that, for example, in this graph, let's say x4 is what is of interest to us, and we want to sort of sample from it. What we can do, perhaps, if we know something like this, like if we know that a structure like this exists, what we can do is we can start instead of directly sampling x4 from its joint distribution, something like this. What we can do instead is start from x1, sample x2, x3, and then sample x4 using x2 and x3. And we saw that this is something called ancestral sampling. Uh, yeah. So this is where we sort of took a step back and we started studying things with respect to a very simple looking PGM, which is this thing, right? So there are just two nodes, Z and X, and there is a edge from going from Z to X. And from the generative view of PGMs, what you can think of this, so let's say if you want to sample X, what you can do is you can sample Z first and then sample X using the conditional distribution Px given Z. So this was the sort of the uh, I mean the simple thing, right? Nothing fancy. Okay. Then we saw that okay, to basically learn the underlying data. So let's say you have been given these two random variables, okay? You have a data sets, you have a data set which contains data points containing Zi and Xi's, okay? You have a P data X comma Z, and you want to learn this underlying joint distribution using a parametric model P theta X comma Z. And what we used was something called KL divergence minimization between P data and P theta. We saw that KL divergence is nothing but a measure of similarity between two distributions. So we just hopped upon it, used it, and went ahead to solve this optimization problem and obtain theta star. And then we sort of simplified the scale divergence term and we did this thing and finally got obtained something like this, right? So, which basically is telling you that, well, if you have data set and all you want to do is estimate this parameter theta, you can simply take log p theta of xi zi, right? Uh, Moreover, you take the log average of this log. So this term is called log likelihood, right? Take the log p theta xi zi, take average of it over multiple instances. You will get the multiple instances from your data set. And once you have that, you can simply uh, 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 what do we say? We can simply use optimization algorithms like gradient descent or stochastic gradient descent to learn these parameters theta in an iterative manner. So yeah, so this is what we saw, right? Okay. Uh,
Yeah, so I was having a query here that which term is called the likelihood and how does it differ from the traditional probability thing?
Likelihood is just, you can think of this term as, I mean, okay, this term likelihood basically comes from Bayes rule. Okay, so in Bayes rule, you have something like Pz given x is equal to P of x given z into P of z upon P of x, right? You have this from your Bayes rule. This term is called a prior. Okay, this term is called likelihood. Likelihood. This term is evidence or partition function, something like that. So likelihood, strictly speaking, means this term, this px given z term, or the conditional term that comes on the other side of the Bayes rule. But
Oh, I
uh,
see. But
but uh, but
here
here,
we do not have.
yeah,
Yeah.
here we do. I mean, it's actually a sort of aberration of notation. Here we are calling this term as likelihood. But I mean, here you are calling this as likelihood because it is actually something like this: P of xi comma zi given theta. So, I mean, you can think of this. I mean, so these terms actually come from the Bayesian literature. So, P theta. So, in Bayesian literature, you sort of try to learn the distribution over theta given a data set. This thing is equal to P of x given theta into P of theta over P of X, something like this, right? Again, this term is your prior, this term is your likelihood, right? So now this Px given theta is sometimes is what we write as P theta of X. And that is why we call this as likelihood, okay? I mean, in our case, it has become P theta of Xi comma Zi. You can think of this as P theta of Xi, sorry, you can think of it as P of, sorry, you can think of it as P of Xi comma Zi given theta, and then it resembles your Bayesian uh, notation of likelihood. However, I don't want to say this thing explicitly because here we have something called Zi as well. But I mean, uh, uh, you can sort of think, does that make sense, what I said?
Yes, yes, yes. Makes sense. Yeah,
You
I
can think
understand.
of this as given theta actually and remove theta from here. This is what is like, it's like, your likelihood in base rule. That's all.
Yes, yes.
Right. So yeah, and so this is how we saw that, Emily. So if you have a data set in which both Xi's and Zi's are available, you can simply, learn your parameters theta to get the joint distribution, learn the joint distribution P theta, and this will work. I mean, this works, okay. But then we say, I mean, of course, I mean, one might ask that, okay, if Zeta is already visible to you, why? I mean, why do you want to, why not? So I can just merge these two and call a new data point, right? Xi comma Zi as some, let's say, Yi maybe. I can like combine these two and call it Yi. Well, I mean, in that case, uh, your MLE, so MLE on such kind of PGM, right? It looks kind of redundant. I mean, what is the benefit of having this kind of structure? If you are end of the day, if you are going to use MLE, what is the use of that at all? Well, it turns out the use of that structure particularly comes in case of latent variable models. So we took this example where you have some hidden variables. Okay. For example, if you see an image, right? There are multiple components in an image. For example, there is an object in the image, there is a position, right? Where is the object positioned in that image? What is the camera angle? And like all these hidden variables or variables that you actually that exist. I mean, of course, when you are clicking an image, all these variables are playing a role, but you don't see that in your data set. I mean, you won't see a data set where you have an image and then you have all these factors written and okay, this was the camera angle, this is how far the camera was from the image, so on and so forth, like things like that. And this is more practical as well, in the sense that this is the kind of model that we would like to learn, right? So in such cases, Z is what we call as unknown or latent variable, which is not available in your data set. Okay, it's there, but you don't see it in your data set. Always think about this example when think about latent variables. Okay, this is quite intuitive in my opinion. And X is what is called as observed variable or the variable that you actually observe in your data set. So in your data set, you are going to observe the images directly. You're not going to observe these factors, right? So this is and such a setting where there is a hidden variable involved, right? This is what is called incomplete data. Okay. Uh, so you don't have access to the full data, or you have a partially observed. I mean, the variables that you are observing is partially observable, right? So this is the kind of framework that we are interested in, and today we are going to sort of see how can we, uh, uh, how can we learn theta in such cases. Okay. So let's get started with that. Uh, so we will start with your elbow, right? let's start with. So we are going to, slowly introduce things, and we're going to slowly see how things. Uh, I mean, you will see. You will see. Okay. So let's start with. Uh, let's start with. So this is. I think ideally this is lecture number 3, right? So this is elbow and EMs. Elbow and well, at least first let's see elbow. Oh, yeah, EM also you'll see this thing also. So this is what we will see, right? Okay. Okay. So let's start. Okay. Now of again let us perhaps uh, rewrite our PGM, which looks like this, right? Okay. Uh, right. So let's say we want to basically what do we want? We want to learn P theta of X. Okay. I mean, eh, for now, let's say that all we want to do is we want to sample from this distribution X, right? And I mean, because we don't have access to Z, we would like to do some maths, or we would like to introduce some framework so that we can learn theta, which will allow us to sample, which will allow us to learn this distribution P theta of X. And once we know P theta of X, then we can think of how to sample from that distribution. Okay. Okay. So let's do that. So how are we going to do this? So I mean, we are going to introduce something called elbow or evidence lower bound. Let's start from there. Okay. Uh, okay. Let's start with it. So I mean, this will be a thumb rule that we won't direct. We will usually work with log of p theta of x. Okay. Log of p theta of x. Okay. Why? Because it is easier to work with log because you don't have to work with multiplications. Instead, you will work with additions, and things will become sort of easier because a log will, I mean, sort of this log function, in my opinion, acts as a filter to remove the redundant terms. So we will work with this thing. Let's try to write this thing down. Okay. Let, what we are going to do is for this setting for at least till EM, we are going to write this thing as log of P of X comma theta. So this is the definition that we are going to use. You will see why we are doing this kind of notation. Okay, we will see that. Uh, okay, because it's easy. I mean, okay. So what is this? This thing is nothing but you can write it as 1 into log of P of X given theta, right? Now you have 1 here, so you can replace 1 with anything, right? I mean, anything which is equal to 1, you can replace it with here. So what will this thing look like? This thing will look like what I'm going to replace this with 1 is I'm going to do Q of Z ln P of X theta dz. Okay. What did I do here? Um, Nothing fancy. Okay. This thing, I mean, if you have to see, this thing is nothing but since this term is independent of Z, this thing will come out, right? Ln P of X theta integral Q of Z dz, right? Which is equal to nothing but ln P of X theta. So, I mean, uh, I have done actually nothing. So this thing is just 1. So I have just multiplied with 1. Nothing fancy here. But why? So this is where you call people also call this Q as a variational distribution in the sense that you have introduced a new distribution with your with respect to your hidden latent variable. Okay. But yeah, I mean, I hope that mathematically there is no problem because I have just multiplied things with him. That's all. Okay.
So I have a query here. I mean, so what this
Okay.
semicolon implies here? So does this mean that this is a joint
So
distribution of?
No. This is not a joint distribution, right? So this is not a joint distribution. This is just to emphasize that uh, this this distribution P of X has a parameter theta. That's all. Nothing else. So it's just so as I said, right? This is equivalent to this thing. These two things are equal.
I
So
see. So does
writing
this
P
mean
of
that
X, yeah.
this is a conditional distribution? Like say, can I
No,
write it
no.
like
This
say
is
log
this
of
is no.
p
This
x
is
given
no,
theta?
no, no, no. This is not a conditional distribution here because theta is not a random variable right now.
Yes, theta is, I mean,
This is
just a
it's
set
just
of
a
the parameter.
parameter. That's
Okay,
all. That's it. Nothing. But we are using this notation for some reason. I mean, we will see that thing why we are doing that. But
okay,
yeah, it's not a random variable of some sort, anything like that.
yes, I understood.
I mean, it's actually, I mean, if I have to be totally honest, even if you think of it as conditional distribution, it's not wrong in the sense that, I mean, strictly speaking, it's wrong. I mean, because theta is not a random variable, but you can think that theta is a Dirac delta kind of function. Like it just takes one value with probability one. You can think of it like that. There's no, I mean, what do you call it? It's not, there's no, because, we are trying to sort of merge this point. So there is a Bayesian view of things and there is a, you know, sort what like whatever ad hoc approach of things. Uh, this is where both of them are sort of coming together, and hence there is usually a confusion that why is this a conditional distribution or not? But and you can think of it like conditional distribution if that makes you comfortable. Yeah, I will just say that. Yeah.
Okay,
Right. So what we are going to do next is we are going to use some sort of marginalization. Okay, let's do that. Um, what should we do here? Let's you have log px theta. Right, so let's do one thing. You do this cube of z, right? You have ln p of x theta, right? You have this thing. I will multiply divide by some quantity, which is p of z given x theta upon p of z given x theta dz. Okay. So I have multiplied and divided it by p of z given x, p theta z given x. Okay. Uh, so you can think of p z given x as a posterior distribution, right? I mean, uh, this was your PGM, right? Uh, what you want is basically p of x given z, right? Uh, you can think of p z given x as this thing into p of z upon p of x. So this thing is your posterior, like this thing is what you call as posterior distribution. That given x, what is the, so it's like, the direction goes from here to here, but you would like to, let's say, infer the value of z given x. It's like posterior distribution, if you want to think of it like that. Nonetheless, so we are just multiplying, dividing by pz given x. Okay. Now what we will do is this thing is also equal to q of z log. So these two, I mean, like these two terms will combine, right? This is p of x into p of z given x. So these two will jointly become what? This will jointly become p of x comma z theta, right? Divided by p of z given x theta, right? Nothing fancy. Now what I will do is I will again multiply divide by q of z here. Q of z. and there is a dz outside. We are not touching that. So what we did was basically combine these two terms to write the joint distribution. The denominator is as it is, and then we multiplied and divided by q of z. So nothing changes. Now what is it that we are going to do? It's the following. So this thing. So I will basically split the log terms basically. I'll show you how. So this is q of z. This is log of. I will basically combine this p with this q and this q with this distribution. Okay. So let me write it down. So this will be p of x comma z given theta divided by q of z, right? Dz plus integral q of z log q of z divided by p of z given x theta dz, right? These are the two terms that we have, right? Now, uh, now this is where it's the this is perhaps the most interesting and like the most important thing that we are going to see. So what do we have? This implies that log of p of x theta is equal to, let's call this term as let's call this term f of q comma theta. Okay, let's call this term f of q comma theta. And what is this term? This term is something that we have seen. Can you recall what is it? This resembles something that we studied last time. So this is q
Yes,
of
so
z.
yes. So here, I mean, we are using two distributions. The one distribution is Z, and the other one is Z given X. So what if
Yeah.
instead of Z, we are using another distribution Z given X? So then, how many extra bits are required? I mean, this is a KL divergence in between the QZ
Yeah.
and then this Z given X.
Yes, exactly. So this is actually nothing but your KL divergence, or what was the notation that I used last time? I don't recall it.
Two vertical
Did
bars. I mean, in between the
I think
QZ
did
and
I
the
write it as DKL, something like this?
yes.
Okay. So this is between Q and P. So
Yes, but then in case of Q it is Z, and in case of P it is Z given X. So
yeah, I mean that is implied. Maybe I will write it down if you get it. So I mean, just want to reduce the clutter because I just use Q here. So this is actually P of Z given X theta. No issues, right? So these are the two terms. Okay. So think about, let's try to like take a step back and think what this equation is. So this is your log likelihood term. Okay. This is your log likelihood term. Okay. That's completely fine. What is this equation telling us? That it is telling us that log likelihood is equal to some function, this f of q comma theta. I hope you can see that I am writing this as f of q and theta because this whole thing is actually a function of two things. It's a function of this variational distribution q, and it is also a function of theta. Okay, and both of, I mean, we'll see. Okay, so think so it's a function of two things. One is a distribution and another is a parameter. Okay, let's just keep that in mind. Maybe that's the first term, right? And there is another term which is KL divergence between Q of Z and P of Z given X. So each of these terms have special names, right? This is your this term is well known. This is log likelihood. We discussed this last time. This thing is called this is the famous elbow. Okay. And this is nothing but your KL divergence, simple KL divergence. Okay. Elbow, what does this thing stand for? This is called evidence lower bound. I will tell you why is this name there. So, okay, let's take. I mean, so this is basically telling you that the log likelihood is actually sum of two terms. The first term is your elbow, whatever this big this weird looking term. This is what we have called elbow, and the log likelihood is sum of elbow and a KL divergence term. This is what this thing is telling us. Okay, now we from if you remember from last lecture, we stumbled upon one property of KL divergence, right? That KL divergence is always non-negative. Okay, if we think about it, so this is always I mean, okay, so this term is always greater than or equal to zero, right? So if I remove this term from the sum, f of q theta, f of q comma theta will be less than ln log of this log likelihood term, right? So what do I mean? So this implies that ln p of x theta is always greater than or equal to f of q comma theta. Is this clear? So
Yes.
nothing nothing fancy, right? This is a positive term. If you remove this positive term, this whole sum will become small because you will only be considering this term. And hence, the sum is nothing but your log likelihood will is always greater than the first summand, right? Uh, and this is I think this is perhaps something that we keep seeing in machine learning or deep learning in general. This elbow term. Why is this called evidence lower bound? Well, if you remember, as I just said in middle, right, that usually in Bayesian inference, Bayesian setting, you want to find this. This is equal to P of x given theta into P of theta divided by P of x, something like this, right? Uh, so this is like a upper bound on log of P of x. Sorry, this is a lower bound on log of P of x. That is why you call it evidence lower bound, and like this term is called yeah, I mean this log px given theta. This thing is also called evidence in Bayesian setting, and hence this thing is called. I mean, you can think of this as evidence, and this is a lower bound on evidence. Okay, so evidence or this log likelihood term is always greater than this term. That is why we call it this evidence lower bound or elbow. So you will keep hearing this elbow again and again in different contexts. It keeps popping up again and again, you know. Okay, fine. Uh, okay, but what is the benefit of this thing, right? Uh, right, let's see. So if I have to write this, so if I write the above equation again, this is f of q theta, this is equal to log of p of x theta minus dkl between q of z and p of z given x theta, right? So, right. So, okay. I mean, what do we want to do? So we want to basically maximize the log likelihood, right? I mean, that is what MLE was also doing, right? That we want to maximize the log likelihood. Why? Because we saw that maximizing the log likelihood, right? Maximizing this thing is equivalent to minimizing the scale divergence, right? This is what we saw, right? This objective is what resulted into this MLE, isn't it? So we want to maximize this thing, but I mean, uh, we don't have access to the hidden variables, right? I mean, we don't have access to our uh, the latent variable z. So what we have done is instead we have found a lower bound on the log likelihood. Okay. We have found a lower bound on the log likelihood. And the claim is instead of maximizing the MLE, will maximize the elbow. Maybe I should write it down. So instead of maximizing maximizing um, instead of maximizing ln px theta, we will maximize f of q comma theta. This is what your elbow allows you to do. Now, elbow is a function of both z and theta, right? Because q is a distribution over z. Q is a distribution over z, and theta is your basically your parameters, right? So this is what the idea is that instead of maximizing this, you maximize this. So why do we want a lower bound on this thing, this log likelihood to for maximization? I mean, why can't we work with, for example, let's say upper bound? Like if we find something which is let's say bigger than log likelihood, why can't we use that to do the maximization? Well, there is a theoretical proof that, I mean, there is a claim that if you maximize f, it will allow you to maximize this log px theta as well. Uh, but yeah, I mean, that is a little bit technical, so I'm going to sort of avoid that proof. But instead, we will see EM, which does exactly this thing. It maximizes this elbow. But another way to look at it is that, well, from this equation, right? If you want to maximize this, right? If you want to maximize this, what is it that you are doing? Uh, well, you are maximizing this. If you maximize this, you are also maximizing this, right? The log likelihood. At the same time, you are minimizing this divergence. So maximizing the elbow results in maximizing the log likelihood. That's that is desired, but it also minimizes this divergence, the KL divergence. And particularly, we saw that there is this inequality between log likelihood and elbow, right? When does the equality hold? Like when will uh, the elbow be exactly equal to this log likelihood? Can
When
you?
KL divergence becomes zero.
Yes, exactly. So the inequality is tight when the KL divergence is zero, right? When DKL between Q and P, this is zero. And when will this happen? When will the KL divergence be equal to zero?
So
This
yeah,
when Q of Z is equal to P of Z given X theta, right?
yes.
So in this case, what will happen is f of Q theta will be exactly equal to log of P of X theta, right? So, so, in fact, this FQ theta would be actually become f of P comma theta, right? Because Q is equal to this thing, P of Z given X theta. So when you substitute Q with P, this log of uh, this log likelihood becomes equal to the your elbow. So as I was saying earlier, right, there are two aspects of, or rather, there are two parameters that govern this elbow. One is this Q and another is this theta. Q basically determines that what is the gap between the log likelihood and the elbow. Okay. So in general, there is an inequality here, but if Q is sufficiently close, right? I mean, you can see this from this equation actually, right? That what is the gap between F and log likelihood? What is the gap between elbow and the log likelihood? It's this term itself. And this term actually depends on what is the value of Q. So if your Q is exactly equal to this thing, so I mean in the sense that if you for a moment, let's think that we keep the theta constant. We are not changing theta. Okay. We we are just looking at Q. So if your theta is fixed and if you substitute Q to be exactly this quantity, your elbow becomes equal to your log likelihood, right? So this is a very crucial observation that that is what sort of you know that is what will lead to the EM algorithm, expectation maximization. Okay. Maybe I will tell it here. I am hesitating a little bit to tell it here, but let me just say it. Okay. We want to maximize this thing. Okay. But we saw that, okay, we cannot have use the information, or we cannot basically uh, uh, use the information of Z by directly optimizing this thing. Okay. We need to learn about, we need to have some we need to accommodate the latent variable as well. And we saw that we what we can do is we can instead work with a alternate objective, which is this elbow. Okay. But the elbow now depends on two things. With one is the Q variational distribution and another is the parameter theta. And we want to maximize this. Okay. And I mean, we'll see that maximizing this will actually leads to maximizing the log likelihood as well. But I mean, we'll talk about it later. So there are two aspects to this. One is the variational distribution and one is the parameter theta. The so what expectation maximization or EM algorithm, what it will do is first it will fix theta. Okay. So thetas are now fixed. So let's forget about thetas. Now I want to maximize this thing, but I can only work with the elbow. Okay. Now, w- but there is a gap between elbow and my log likelihood, as we can see here, right? If theta is fixed, still there is some gap. Even if you remove theta, there is this gap, right? Which you cannot, I mean, which will still exist. So first, what I will do is first I will reduce this gap between log likelihood and elbow by substituting Q of Z to be exactly equal to this P of Z given X theta. Okay, where theta will be fixed. Once that happens, your elbow becomes equal to your log likelihood. Okay. Now, once that has happened, what I can do is now I can fix my distribution Q. So now Q is fixed, and I will optimize on theta using gradient descent or gradient descent, whatever. Does that make sense? Is that giving you some intuition? I mean, it's very hand wavy right now because I haven't exactly explained how exactly all these things are done, but I am trying to give you a intuition as to what EM algorithm will do. It will do two optimizations. First, it will optimize Q by by making it equal to this distribution so that KL divergence term dies out and both of these things become equal. Once these two things are equal, it will fix Q and then optimize only on theta, and like theta will be optimized, and then we will alternate, right? We first so like first we'll fix theta, substitute Q to be this thing, right? Then we will fix Q, optimize theta by maximizing the elbow. Again, we will fix theta and substitute Q to be this thing. Again, do optimization on theta and so on and so forth. So that is those are the two steps of EM algorithm, expectation maximization. So there is a E step and there is a M step. We will see that thing. So both of them are actually doing one optimization, one with respect to Q and another with respect to theta. I'm just trying to give you an intuition. It won't be very exactly clear that what will happen, how it will happen, but I'm just trying to give you an intuition that look, this is how things are going to turn out next. Yeah.
So I could understand the thing still here that Qz should be equals to the Pz given x and then theta,
Mm.
right?
Mhm.
So that this FQ Q theta becomes equals to
Mm.
the log likelihood. That's
Right.
okay, but then Q
Mm,
itself is not known, and we took any distribution over Z. So QZ
mm.
was, I mean, so Q was completely unknown. So how
Right.
to
So
get
so
this?
that is why I said that we will substitute Q with this distribution, P of Z given X theta.
But
So
then,
of course, as you said,
but
right,
then,
Q is unknown to us. Q is
yes,
unknown to us,
yes.
completely unknown to us. And
But then
because we
Z
just
is
introduced it, because we just arbitrarily introduced Q, right? I mean, I mean, this could be anything for all purposes. This could be anything. Okay? We haven't imposed anything on top of it. But what we know is once Q of Z is equal to this distribution, it could be anything. It could be this also, right? And in that particular case, when Q of Z is equal to this P of Z given X theta, in that case, we can this term will die out. These two will become equal, and then we will optimize theta. Uh, is that make? I mean, I don't know. Does that make sense?
yes. So, but Q is unknown, and so is Z. So even though the distribution
See,
Q is
Z
not
is
known
a
to us,
random variable. Z is a random variable. Q is a distribution on that random variable, and that is unknown. Yes, that I agree.
so yeah, so even if, I mean, to determine the value of, say, to determine Q distribution, I would be say taking the help of the P distribution.
Yes, this
But then while
distribution.
taking the help of the P distribution, I require this
Mm,
thing, say Z given X, and Z is totally unknown to us.
mm.
So neither we know the left hand side nor we know the right hand side. So
No,
I
no,
mean,
no. So this is something that we will be able to calculate.
uh, how?
Okay.
Because Z is not
So
known. Z is a latent
no, no.
variable in the set.
This is a latent random variable, right? So for example, in case of, I mean, in certain cases, you will be able to determine this distribution particularly. So it's like, uh, P of Z given X. Okay. This thing is equal to what? This is equal to P of X given Z into P of Z upon P of X. Is that right?
Yes.
Now, P of X given Z is something that we can use from our graphical model. Like the PGM will somehow, PGM will, we can take help of PGM here to get like what is the value of P of X given Z, right? And P of Z is a prior distribution. Like it's a prior distribution. Now, prior distribution is something that we will have to assume. Like, for example, we can assume that P of Z is Gaussian, for example, something like that. Uh, does that make sense? So PGM is, we will take help of PGM somehow to calculate this P of X given Z. I mean, for example, in if you have seen these Gaussian mixture models, right? Where what you have is for example, you have multiple Gaussians. Like there are, let's say, for example, there are two Gaussians. One is here and another is here, and they are mixed with some probability in the sense that so the your joint distribution is like P into Gaussian, let's say mu one comma sigma one plus one minus P into normal mu two comma sigma two, something like this. In such cases, your latent variable is basically like you can think of this as there are two centers, like there are two clusters, one at mu one and another at mu two. These will become your latent variables. So, for example, if I know that the sample is taken from mu one, this will become my P of X given Z, right? And if I know that the sample is taken from the second cluster or mu two, this will become my P of X given Z, something like that. So P of X given Z is something that you will be able to calculate. And yeah, I mean, so, and hence you will be able to calculate this thing, P of Z given X totally.
Okay, so probably you would also be talking about that how to get the latent variables and how to identify all the G's,
Yeah,
all the jets. Okay,
yeah.
okay.
Yeah, we will talk about that. In fact, this is one point where, you know, mm, these things fail. This is why EM fails. Because many times, I mean, in simple cases, you will be able to find out what this P of Z given X is. Okay. But we will see that the main problem with EM algorithm is that in complex scenarios, this distribution is something that we won't be able to evaluate at all. So P of Z given X is something that we can evaluate in simple scenarios. For example, in Gaussian cases like Gaussian mixture models, it is very easy to evaluate, compute this thing. However, in case of, let's say, complex things like neural networks or something like that, this becomes intractable. You won't be able to calculate this, and hence everything falls apart. You won't be able to use EM. But I mean, even for okay, maybe for time being, you can assume that you are able to calculate this P of Z given X. Okay. In that case, is it clear that what I'm trying to say that we can do a double optimization? First, optimize on Q to make these things equal, and then optimize on P to make this thing equal. So this is something that
Yes, yes, yeah. You went on mute for some time in case you are speaking something. Now you are
okay.
mute. Yeah, yeah, audible now. Yes, yes.
Okay, okay, okay. So so let's see. As I said, that let's discuss that EM algorithm, right? So this is expectation maximization algorithm. So this is something which is so usually I think people don't talk about EM algorithm when teaching generative modeling, but I feel that EM there is a flow to all of this, right? Starting from MLE, coming to ELBO, then going to EM, then we will see that the shortcoming of EM, and then we will see the variational inference, and then going to all the way till VAE. And from there, things will become even more sophisticated and so on and so forth. But there is a flow to it, and I want to sort of, uh, you know, uh, uh, like sort of, I want to just make sure that that flow is maintained, and we should know that why something is coming uh, when the previous, like, what is the motivation for the next thing, basically, right? So let's start with this expectation maximization or EM algorithm, right? So what is this algorithm? So it's very simple. So let's assume that we can find P of Z given X with theta old. Let's call it old theta analytically. So of course, as you see here, right, that we assumed it initially only that this thing is something we can calculate. So the point you were saying that you cannot perhaps compute this thing, it goes in assumption that we are assuming that we can find the value of this distribution analytically, in the sense that we can do some calculation. Analytically basically means that we can do some maths and find this distribution. Let's assume that. Okay. So, mm, uh, so so what is your so as I said, right, if you substitute Q of Z to be equal to this P of Z given X theta, right, these two things become equal. This is what we are going to do. So like substitute Q of Z equal to P of Z given X theta old. Okay. So what will our elbow become? So this is F of Q comma theta. This is what? This is Q of Z log of, I mean, remember what was this thing, right? So F of, this was Q of Z log of P of Z X comma Z theta upon Q of Z, right? So log of P of X comma Z theta over Q of Z. dz, right? This is what our elbow was. So this can be written as integral of q of z. So I will split the log, right? This will become log of p of x comma z theta dz minus integral q of z log q of z dz, right? So again, what will the now if we substitute q of z to be this thing, right? This thing, what will it become? So this is p of z given x theta old, right? ln p of x comma z thetas. Remember, this is theta, not theta old, minus integral p of z given x theta old, right? ln p of z given x theta old dz, right? I hope this is clear. So this term, so look at the first term, right? This term. Look at this term. What is this thing doing? This thing is a function of both. First thing to note here is that it is function of both theta old and theta. Okay. This is something that we should quickly note here. Okay. So let's call this thing, let's call the first term to be a q function, q of theta comma theta old. I hope you understand why I am writing theta comma theta old, because there is a theta old that we have from previous iteration maybe. Okay, that is something that we computed in the previous iteration or we started with it, something like that.
Or
That is
probably
why
we
we
are,
are,
yeah,
sorry.
or probably we are trying, since the purpose is to optimize theta, and assuming that the theta
Yes,
old is given. So
yes,
iteratively,
yes. So,
probably we are
so
trying to find, yeah.
yes, so theta old is coming from your previous iteration. Okay. So that is why we are calling it the old theta, the one from the previous iteration. Okay. And there is another theta, this one. There is another theta, uh, this theta, right? Which you can still optimize on. Okay. So just note very explicitly that there are two thetas here. One is theta old and another is this theta. So this Q function is a function of both theta and theta old plus this is nothing but entropy of this P of z given x theta old, right? So this is just h of uh, maybe I will just write it as Q because Q is equal to this P of whatever, right? So your this is your f of Q theta, right? Now, uh, so basically, uh, if you think about it, right? So this entropy term doesn't contain any theta term, right? This term is constant with respect to theta. Okay. So what if we want? So if we want to, so what we have done is, so we have first substituted q to be equal to p of this z given x theta, right? Theta old rather. Okay. Now we want to optimize on theta. So if we want to optimize on theta, this term is not going to play any role, or only this q term is going to play that role, right? Is that clear? I hope there is nothing that is not clear here.
Yes, so the second term is the entropy term, and
Yeah, and the first term is yes.
second term does not depend the old value of the
On
theta. So yeah,
no, so the second term depends on the old value of theta. It doesn't depend on the current, like the theta
current
that we want
value.
to optimize on. Yeah.
Yes, yes. Yeah.
So, uh, so if we want to optimize on theta, all we need to work with is this q function, right? This q of theta comma theta old. Now, what is this q of theta comma theta old? What is this thing? This thing, if we look at it, this is p of z given x theta old log of p of x comma z of theta, right? dz. This is nothing but this is actually an expectation, right? This is actually an expectation under p of z given x theta old log of p of x comma z theta, right? Because just by definition of expectation, yeah, this is the term and this is your function. So this is expectation. So now you can what you can do is you can optimize. So basically you sample a lot of. So now you can like basically optimize. So this is a function of just theta. I mean, you can optimize. You can take the derivative of this with respect to uh, uh, theta and maximize it. That's all. So this is what eventually the EM algorithm is. So the EM algorithm, maybe I should use some other color. So the EM algorithm is as follows. There is a E step, right? There is a first and foremost, there is a E step. What is this E step doing? E step, E step basically says compute, compute Q of Z, which is equal to P of Z given X theta old. Okay. And basically using this, what are you going to evaluate? You are going to evaluate this expectation, expectation under expectation under P of Z given X theta old uh, log ln P of uh, X comma sorry X comma Z theta. Okay, this is your Q of theta comma theta old, right? And then there is a M step. There is a M step. In M step, you basically find theta, which is equal to arg max over theta of Q of theta comma theta old. So that is why this is called expectation maximization. That in the first step, you are actually computing an expectation, right? This is the expectation term. And in the second step, you are maximizing it using on theta. This is your EM algorithm. Any doubts still here? If you have any doubts, I think this is the right time to ask.
Yeah. So can you summarize the E step? What are we doing in the E step?
So in E step, uh, let's go back here. Remember that there is a gap between the elbow and your log likelihood. And what is that gap? That gap is the scale divergence term. And when will this gap vanish? When Q of Z is equal to P of Z given X comma theta. Okay. What the E step is doing is it is basically vanishing that gap. It is basically saying that substitute Q of Z to be equal to P of Z given X comma theta old. Okay. So that at theta, so the gap is basically vanished. Okay. And we saw that in that case, your elbow basically decomposes into two term. One term is actually independent of theta, so we don't worry about this term, so we can ignore this term. We can just work with the other term, which is this Q function. And this Q function turns out to be an expectation. So the E step is first saying that, okay, compute Q of Z to be equal to this P of Z given X comma theta old, okay? And then compute this Q function, which is an expectation, okay? This is the E step. M step,
Yes.
what is the M step doing? It is just optimizing theta on this uh, uh, on this Q function. That's all.
Yes. Yes. Clear. Yeah.
Okay.
Thanks.
Now, with this explanation, it might be like, okay, the math is working out, but it's not very intuitive, perhaps. Maybe it might look like that. And honestly, to me also, the EM calling it the expectation maximization, it's for me also it has been difficult to comprehend it like, okay, there is a E step and there is a M step. Maybe what I will do is I will perhaps explain this whole thing in such a way that it becomes perhaps more intuitive in some sense. Okay. So let me do that. And for to me, that perspective I will give you that that's alternate maximization perspective is sort of more intuitive to me. Okay. I will just write those things down. So what is it? Uh, maybe this is alternate view of EM. Let's look at that. So, so let us try to first think about this. I will try to use a pictorial view so that maybe it becomes clear. Okay. So let us say that, let me draw that first. So, so let us say this is your ln p x theta. This is your log likelihood. Okay. Then what you have is something here. Uh, so this log px theta, as we saw here, right? It is log px theta is actually sum of two terms. One is elbow and another is the scale divergence, right? So 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 there are two terms to it. There is this first term, which is your f of q comma theta, right? Which is your elbow, right? This is your elbow, okay? And there is another term which is your Kl divergence. So dKl between q and theta. This is the picture, okay? That you have first you have this your whole log likelihood which you want to maximize, but you saw that you cannot make use of the latent variable in this naive form, so you came up with this lower bound which is smaller than this thing. I mean, I hope the size is clear, right? This is bigger and this is smaller, so it's a lower bound, but it's a sum of this elbow and there is the scale divergence. Oh, sorry, this is p, okay, and this is scale divergence term. So in the first step, what you are doing is you're what you're doing is you're based. So the E step, if you want to think about the E step, what is it doing? It is doing nothing, but it's simply making this gap zero. Okay. So how do perhaps, yeah. So this is the gap in your elbow and the log likelihood. So what the E step is doing is it is slowly pushing this value to reach this point. This is the E step. This is your E step. If you want to think about it, you can think of it like this, that there is a log likelihood. Some part of it is your elbow and some part of it is your KL divergence. The E step is doing nothing, but it is simply increasing your log likelihood so that it becomes equal to your, so it is simply maximizing your log elbow so that it becomes equal to your log likelihood. Okay. This is the E step. Okay. So, I mean, in this, like, if you want to think of it, uh, like, you can think of it like this, right? That once you, after E step, basically after E step, this whole thing will become f of q comma theta. The KL divergence, this dkl will become equal to 0. This is basically your E step, okay? Uh, is that making sense? Like, I don't know, does this picture make sense?
Yes. Uh,
Right.
yeah. Except this fact that we want to minimize the KL divergence value, and to minimize the KL divergence value, we are maximizing something. So to minimize DKL, we are maximizing something, and probably we are
Yes.
maximizing the expectation thing, and which is not, I mean, so very intuitive from this diagram that we want to reduce this DKL and by maximizing something.
Uh, s- no, so the only way you can, so KL divergence cannot become negative, right? So the only way you can minimize this is by maximizing this, right? I mean, uh,
Yes.
I mean, there is no other way.
Right, right. So
And if you want,
where is next step in this diagram?
yeah,
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 please keep going.
I'm coming to that. I'm coming to that. So let's keep this thing in mind, right? Let's keep this picture in mind, and then we can think of M step as well. So this is the new, so I will draw the same thing, but in a different context now. So let us say that this is your theta axis. Okay, there is this theta axis. Okay. Now, let us say that there is a log likelihood function on top of it. Okay, there is some log likelihood function like this. This is your ln p x theta. Okay. Now, let us say that at a given time instance, you are at theta old. Fair, right? You are at theta old. Now, at theta old, at this particular theta value, there can be different values of. So maybe I will. So there can so different for different. So remember that the elbow is function of both, right? It is a function of q and theta. Now, what you have done is you have fixed theta, right? What you can do is there can be different values of the elbow, right? And since elbow is always less than this log likelihood, so there can be different. So there could be something like this. This could be one function representing elbow to one q1, right? So let's say this is like q1. There could be another elbow, something like this. This is like q2, right? There can be some other elbow, something like q3. There can be something like this q4. Is that fine? Like corresponding to different q, there will be different elbows. Does that make sense?
Yes, yes.
Okay. So let's take one such q, right? Let's take maybe for example, let's take this something like this. This is like f of some q comma theta. In general, it will look like this. Okay. But now what you are doing is you have fixed you have fixed this theta old, and you're saying that find a q which maximizes the value of this elbow for this theta old. Okay. Now let us bring this picture here, right? This is so here you can think of it like this, right? This is this value of the log likelihood, right? This is the current value of, sorry, this is your current value of your f, right, at this particular theta. So you can think of, uh, so this is your f, this is your f, right? This is your the ln p x theta, right? And this is your the remaining thing. This thing is your DKL, KL divergence. Okay, is this clear? So at this particular theta, this is how the picture will look like, isn't it? For a particular Q.
Yes.
Now you're saying that okay, for on this line, you want to basically push this thing up, right? You want to maximize your uh, elbow for this particular value of theta. Is that like does that make sense again?
Yes, yes.
So what will you do? So you will say that, okay, fine. I will. So basically, that Q is equal to this PZ given x theta. That is when the KL divergence will become zero, and you will basically get a curve like maybe something something like this. This is touching, okay? Something like this. This is touching, let's say. I mean, it's not looking, but okay. I mean, I have made it touch. So this is f of p comma theta. When you substitute q to be equal to p, the Kale divergence thing, this thing will become zero, and this whole thing will become your this thing will become your the elbow f of p comma theta. Is that fine?
Yes.
Right. Now, what you're saying in the this is your E step. Till now, you have once you have done this, this is your E step. Do you agree?
Yes.
Now, what is the M step doing? The M step, what that thing is doing is it is saying that okay, fine. Now you have fixed the Q. So basically, fix the variational distribution, that is Q of Z, which is equal to P of Z given x comma theta, right? So now this curve is fixed. This curve is fixed because the distribution determines which curve will come, right? This curve is fixed now. Now you're saying that on this curve, maximize obtain theta so that this value is maximized again, right? That is what the M step was doing, right? You are saying that now you have this q theta comma theta old, which is nothing but, I mean, you can think of it as f directly because this thing doesn't depend on theta anyway. So you can say that in the M step, what you're saying is that on this curve, do a gradient ascent and maximize the value of this f. So what will you do? So what will it do? It will do some gradient ascent, and where is this value getting maximized? The value of f on this curve, where is it maximized? It is maximized at this value, right? This peak.
Ye- Yes. Yes.
And this is where you will get your new theta, the current theta, let's say, right? Right.
Yes.
Does that make sense? That now first you maximized with keep holding the theta fixed. Now you said that okay, now I am holding the curve fixed. So there are two things. One is the value of theta, and then there is this curve. If you fix the theta, there are multiple curves. If you fix the curve, there are multiple thetas, right? Like if for example here you fixed theta, right? Then there can be multiple curves here. On those curves, you found the one curve that maximizes the value of f, the elbow here, this particular thing. And now you are saying that okay, now hold this curve fixed and now vary theta. So theta went here because the value of this curve is maximum at this theta. And now you do again the same thing. Now you ask that well, now you have fixed. I will again fix my theta here. Okay, I will again ask. I will again ask to find the value of new distribution q so that it is maximized. So maybe you will get a curve like this now, something like this, right? Here it is maximized, and then you will do again a gradient ascent here, which will take you to this new theta again. This will become your new theta, and you will reach here. So do you see how this maximization is taking place? So first you are holding the theta fixed, and you are optimizing over different curves. You find that curve. Once that curve is found, you say that okay, hold on, now keep this curve fixed and maximize over theta. So you find this new theta. Now on this new theta, you again ask that find the new curve that maximizes the value of the elbow for this particular theta. You get this new curve. On this new curve, you ask that, okay, find the value of theta, which maximizes this curve. So you get this new theta, and so on and so forth. So you can think of EM algorithm in this way, that there are two optimizations that are happening. First, you are fixing the theta. When the theta is fixed, the curves there can be multiple curves. You find the one curve that maximizes the value of the elbow at for this particular theta, where there will be only one curve like this. And then you say that, okay, fine, this is maximized now. Then hold this curve fixed, maximize on theta, get the new theta. Now on this new theta, again, find the new curve And again on this new curve, find a new theta, and so on and so forth. So the EM step is actually doing this thing. So E step is first, I mean, I have repeated this multiple times, but again, I will say it, that E step is fixing theta and maximizing, picking up the curve, which maximizes the value of elbow for that particular theta. Then the M step is basically saying that, okay, now hold the distribution, the curve fixed, the distribution fixed, find the value of theta that maximizes the value of the elbow. And that is why I was emphasizing many times that elbow is a function of both Q and theta. The the change in Q will give you new curve, and change in theta will basically optimize that curve. Uh, Now, I mean, I have said a lot of things. Is this clear? This I think
Yes.
should be it should be very. I mean, it's not intuitive, but I think after this is one explanation that I find very intuitive. At least for me, this is the most intuitive explanation of EM algorithm, because in equations you cannot see this thing maybe like what is it that is happening. Maybe after you like do this thing a lot, you will start seeing those things in equation itself. But I think to start with, this diagram or this kind of diagram should help you to understand what it is.
Yes. So, I mean, through this diagram, the entire concept is very much clear. So, the only thing is that we did not, I mean, use the properties of a logarithmic function. Like it will never come down like this in this diagram. So, can we exploit that property somehow so that we
The
can stop?
logarithm function, I mean, the log function actually, it's easy. I mean, the log function helps in mathematics, okay? I mean, if you look at it, because of log functions, so as I said, right, it acts as a filter. For example, your elbow had these two terms, right? This ratio, it had this ratio. But because it was log here, right, you were able to discard this term here. I mean, that is how that is why log helps in calculation rather than the final uh the overall idea. It helps more in calculation. Yeah.
So I mean to say that beyond a value of the value of the theta is not going to improve. So I mean beyond a fixed
Huh.
number of the cycles, probably we can stop the algorithm
Yeah,
there
yeah, yeah.
itself,
Oh,
knowing that.
algorithm. Oh, I heard of logarithm. Sorry, sorry. So I heard it as logarithm. So yeah, of course. I mean, you will have a like stopping condition. So for example, if theta minus theta old, right? This norm perhaps is less than equal to some epsilon, you will just stop or just stop. There will be some condition like this.
Yes, yes.
So just keep iterating between E and M step again and again and again. After one point, it will converge and this condition will be satisfied, and you will stop. I mean, there are other proofs as well that, I mean, you can always show that, that so like some of the very commonly asked question is that, well, can you prove that ln px theta new, let's say the new theta, whatever you get, is greater than equal to ln px theta old using this algorithm. So you are doing a EM step, fine, but can you prove that this will always happen? So if you can prove this, it means that the EM algorithm always improves your log likelihood, right? Isn't it? I mean, I hope you
Yes.
can. This is what it is saying. So there can be someone can ask you questions like this, that can you prove this thing? So I mean, it's actually easy to prove. You can uh, maybe I'll leave it to you. Just think about it. Maybe it's a homework like thing. You can think how you can prove this thing. If you can prove this thing, I think you have understood the maths as well as the underlying intuition. Right. So this was expectation maximization, right? Okay. Yeah. So, right. But as I think you said earlier, right, that There is a obvious problem with this algorithm. What is that problem?
We do not know, I mean, Z, probability of Z given X beforehand.
Yeah. The main problem with this whole setup is that uh, P of Z given X theta is generally intractable. Intractable. I mean, you can it is calculatable when you have simple cases like, for example, you have, let's say, something like uh, uh, something like maybe Gaussian mixture models or Bernoulli mixture models. These kind of steps, you have those things. You can easily calculate your uh, these things are calculatable in those cases. But for example, if you have neural network, for example, you cannot. I mean, why is this intractable? You will see this a lot that they will say that this distribution is intractable. What do we mean by saying that this is intractable? Well, P of z given x, right? This is equal to what? This is equal to P of x given z into P of z upon P of x, right? To calculate this entire distribution, you need to know this thing, and this thing. These two are calculatable. These are tractable in general. You can do something or the other to make this tractable. But this thing is always, most of the cases, it's intractable. Why is this intractable? Why is P of x intractable? Well, the P of x, this is integral equal to P of x comma z dz, right? This is this is how you will calculate P of x, right? Basically
Yes.
marginalize out the z. Now here x, like x comma z, these are like higher dimensions. So maybe like x belongs to some r d1, right? And z belongs to some r d2. And you're saying that you have to do this whole integration over RD2, let's say, something like that, right? And this integration itself is intractable because RD2 is a infinite, like it's a vector space with infinite support, right? You cannot integrate over the entire space. I mean, even if it is R, it sometimes get difficulty in doing the integration. Think about RD2 where you want to integrate this function, this joint distribution, right? It's that is why they say that since we cannot calculate this integration, the distribution is intractable. And for this reason, we usually don't go for EM algorithm. So, so what is the problem? So this is the main problem. Okay, I mean, I already said that what is the problem. The problem is that P of Z given X, this thing is generally intractable for complex cases. But so what is the solution? What is the solution? What is the solution? The solution is to basically restrict Q of Z to class of distributions to the class of distributions which are tractable. What do I mean by this? So you remember in the E step, we always substituted Q of Z to be equal to this distribution, right? And we did that EM step. But if it is intractable, what we are saying is that, well, in those cases, what we are going to do is we will simply restrict Q of Z to the only to the class of distributions which are tractable. Okay. And this is what is called uh, as variational inference, which we will see in the next class. So the idea is to basically restrict Q of Z to a class of distribution which is tractable, from which we can easily sample and calculate and things like that. And once, so this restriction brings in some other complexities because we won't be able to use the EM algorithm anymore, right? Because EM algorithm assume that you can make the scale divergence completely zero. But if you're restricting Q to be in some class, like some class of distributions, the scale divergence need not go to zero always, right? It might not be, it might be some non-zero quantity. So EM algorithm won't work in those cases. So in that case, what we will do is look at something called variational inference. Okay. And like we will see how what happens, how things go when you do that. Uh, yeah, does that make sense? I mean, I said a lot of things. I don't know.
Yes, so except that, how to show that a particular, distribution is intractable, or whether the calculation can really be done or not. How it,
So
there must be some.
intractable distributions, I mean, if you can calculate it on paper, it's tractable. Otherwise, it's intractable. Simply. So it's like, uh, you know, uh, for example, integration over RD, these kinds of terms you can never calculate. I mean, at least generally you cannot calculate. I
What
mean, so but
what we
just
have
you can just
indefinite.
think of it. You can just think of it. Can I calculate this distribution? If you can, then good. If you cannot, then it's intractable.
Okay,
Yeah.
okay.
I cannot give you any better. Uh, I mean,
Like say,
generally, most of the distributions are intractable. Let me just say that most of the distributions are intractable. There are very
we
few that
can.
are tractable. Yeah.
Okay, the limit of an integration could be say from minus infinite to plus infinite. So what's
Yeah.
the meaning of integrating a distribution in R2, say? So does this mean that I would be using double integration
So no, so
with
integration
the.
of this type. For example, you want P of X. So to calculate P of X, you want to integrate P of X comma Z dz. You are not integrating over X. You are integrating just over Z. Can you do this kind of integration?
So what is,
Ma-
what is making this integration intractable? Which thing is making this thing, tough to calculate?
What is it that is making this thing interactive? Because I mean, think about it, right? Like there's a this RD space. You want to basically go at each point in RD2, which is infinite, right? I mean, you cannot go at each point in RD2, calculate the value of P of X comma Z, see the area under it, and like do that integration, right? I mean, this is a infinite support basically. That is one thing that is restricting you.
Mhm. So probably you would be explaining this thing in the next lecture. By discussing this variational inference.
Yes, yes, we will see how variational inference helps us in alleviating this problem. Yeah.
Okay,
I mean, again, we
appreciate.
will we will keep working with elbow only. Okay. I mean, what we are going to see next is perhaps the why we introduced all that PGM, right? That the whole idea of PGM that we used and did, right? We are going to use that. I mean, we are going to take help from that to basically overcome this problem using variational inference. We will see that, yes.
Please share these notes also.
Yeah, yeah,
Students.
I am sharing both my notes as well as the lectures in the file section. Both of them
Yes,
are available.
yes, yes. Yeah. Thank you so very much.
Okay. Thank you guys. Thank you for joining. Um, we'll see
Bye.
you in the next class. Yeah.
Yeah.
Bye.
Bye.